Hello. In this work, we present a method for expediting the mapping of a previously unseen indoor environment based on learned experience. The problem of indoor mapping is stated as reaching a desired level of exposure in minimal time. We propose to expedite the process by incorporating the structural statistics of the environment in the form of a motion planner trained by reinforcement and a map predictor trained in a supervised manner. The motion planner learns a policy directly from the statistical data, and by predicting statistically informed observations, the map predictor aids the motion planning as well as the map construction process. Two distinct floor plan datasets were used, differing in the level of diversity of the structural features of the maps. We began by training and incorporating the motion planner. The motion planner was realized using a standard convolutional neural network. Our training algorithm of choice was proximal policy optimization. The motion planning network was trained on specific pairs of dataset and desired level of exposure. Let's examine the performance of the trained motion planner compared to a cost-utility frontier-based algorithm. The left figure shows the traversed path and final map constructed from observations of the frontier-based algorithm. To the right is the same but obtained from the trained planner. The mapping durations below demonstrate how statistically induced motion planning can significantly shorten the process. The second statistical model added to the mapping system was the map predictor. The map predictor was implemented as a convolutional autoencoder which takes a set of partial observations and outputs the occupancy probability in each cell. A different instance of the network was trained on each of the two datasets. In the final setup, the two learning-based methods were combined. In this case, the pre-trained map predictor was incorporated into the training of the motion planner. Let's see an example of how the added map predictor boosts the map construction. Here we can see the mapping of an environment belonging to the second of the two datasets that were examined, as shown in the right figure. The center figure contains the constructed map obtained by combining the observations shown to the left and the prediction. At the top, it can be seen how the map predictor is capable of substantially enlarging the exposed areas, in this case by nearly 65%. Now let's examine the combined effect of the trained motion planner and map predictor on the mapping duration. The left figure shows the traversed path and the final map constructed from observations of the frontier-based algorithm. To the right are the results from the trained planning setup, where the leftmost figure depicts the executed path and corresponding observations, and the rightmost figure shows the prediction-based constructed map. The mapping times below, which are typical for this dataset, demonstrate how combining both of the trained models can yield a reduction of up to 75% in mapping time. In conclusion, we employed two different learning methods with the aim of fully exploiting available statistical data of the environment for the problem of indoor mapping. In our work, we demonstrate how this combined setup produces paths up to 4 times shorter than a baseline frontier-based algorithm.